Exercise number 28 from the textbook asks us to evaluate the surface integral over S of f dot ds. Notice that this is now a vector field we are integrating. For the vector field f given by yz, zx, and xy as those three components, where S is the surface z equals x sine y, where x goes from 0 to 2 and y from 0 to pi, so we have this nice rectangle with upward orientation. So remember that evaluating a surface integral like this is also sometimes phrased as computing the flux of f across the surface S. That is an equivalent way of saying this. It just means evaluate the surface integral. And flux has lots of physical and geometric interpretations. There are a couple of ways of going at this thing. And I will first do the one using the straightforward formula from the textbook. Then I'll show you how to set up the problem with a basically just with an expression for ds there. The formula from the textbook for the double integral, I should say the surface integral of f dot ds. This is formula 10, I believe it was, whichever one I referenced in my notes. There's a formula that says, okay, well, that's just the double integral over the domain D. And this only works when S is a function, but Z is a function of X and Y, so this is good. So we have the double integral over the domain D, this is the domain of X and Y, of negative P times the partial of Z by X minus Q times the partial of Z by Y plus R dA, where P, Q, and R have their usual meanings of the components of the field F. So if you use this method, then we basically just have this very direct substitution here, where we see, okay, we have the negative of P. Well, what's P? P is YZ, all right? But we don't want to write Z here. We want this to just be in terms of X and Y. So what's Z? Z is X sine Y. So YZ, Z is X sine Y. We have Y times that, so we get XY sine Y. There's P. Now we have the partial of Z by X. So we look at Z, take the partial derivative of this with respect to X. Sine Y is constant, so that's what we're left with there. Here we go. Minus Q. Q is Z times X. Again, Z is X sine Y, so multiplying by X, we get X squared sine Y. There's Q. The partial of Z by Y. X is constant, so we differentiate sine Y and end up with X cosine Y. And then we have plus R. R is simply XY. Didn't really need the parentheses there, I suppose. And we have all of that dA. And that is basically it. The rest is simplification. The domain D we are given as this rectangle. So that is the integral from 0 to 2 of the integral from 0 to pi of, let's go ahead and simplify some of this stuff. XY is positive. Let's pivot that to the front just so we have fewer signs to write. So we have minus XY sine squared Y minus X cubed sine Y cosine Y dA. And this is now something that is a chapter 15 style double integral. You could probably work through that just fine. It is a little bit messy, so let me point out one thing that'll make it a little bit easier. We like it when integrals are separable, and looking over this, there's nothing really that we can factor out of every term. I mean, there's an x, but that still leaves, some x's behind here, so that doesn't help. But each term individually is separable. So if we split this integral up term by term, and then separate each of those integrands, you'll have the integral from 0 to 2 of x dx. Oh, I just realized, if this were a live class, this is where I would say somebody should have stopped me. But none of you can stop me because you were watching this later. This should have been dy dx because I wrote this as an iterated integral rather than a double integral. So we have dy dx here. Sorry about that. So when we separate this, we have the integral from 0 to 2 of x dx times the integral from 0 to pi of y dy. This is our first term, right? And then we have minus, looking at this, we'll get the integral from 0 to 2 of x dx times the integral from 0 to pi of y sine squared y dy, minus the integral from 0 to 2 of x cubed dx times the integral from 0 to pi of sine y cosine y dy. So we have, this is kind of using a divide and conquer sort of technique here. We've split this up into a combination of 6 individual integrals. 4 of them are very straightforward. 2 of them are even the same. This one, this one, this one, and this one are, very trivial Calc 1 integrals. This last one here is also a Calc 1 integral, but using a substitution rule. This one right here is a Calc 2 integral. This is a nice little exercise. I recommend actually, if you do have a little bit of time, go ahead and work through this whole thing because it is a nice exercise to go through. You might notice that we are going to need to use a couple of early Calc 2 techniques here. Nothing too fancy or strenuous, just a couple of things to work through. And that is like I say, it's a nice exercise to work through. I encourage you to go through and confirm that, assuming I did everything correctly, this works out in the end to pi squared over 2, which is cleaner than we have any right to expect. But we are fortunate that a lot of things simplify nicely and combine and cancel and reduces down to quite a nice little thing there. So we have this surface integral. So there's a vector field described by this function here. And the surface z equals x sine y above this rectangle. We're told this is upward orientation. This is good. If it were downward orientation, you want to watch for that. And really, that's just going to mean that we need to throw in a negative sign here. You could switch the signs on these, but realistically, the easiest way to handle things safely is to just say, okay, well, the downward orientation is the opposite of the upward orientation, so just put a negative sign in front and then calculate the rest as you go. So if this were downward orientation, we would just have negative pi squared over 2 at the end. But that's basically how that works out there. Now, I mentioned there was another way to approach these, and this is if you're trying to memorize formulas and you would like to memorize as little as possible, there is another approach you can take, which is to simply get an expression for what ds is, this differential surface. It's like an oriented surface area. It has built into it a normal vector, a unit normal vector, together with a differential surface area. So it's like a weighted surface area or a weighted normal vector or something like that. It's hard to describe. But this we can define as being negative partial of z by x, negative partial of z by y, and 1. That vector there. So that is this with a dA to handle the, like I said, the differential part of that. So this is a little bit smaller and more compact. Notice that with this expression, if we were to take the magnitude of that, right, we'd have the square root of z by x squared plus z by y squared plus 1 squared, and that whole square root times dA is the expression I gave for ds, the differential surface area. So this actually works out pretty nicely here. The way we would apply this is it basically comes up through the application works out much the same way. It's just a what you plug in where. So when we have this double integral over s of f dot ds, the idea is that you would just substitute as you go here. We'd integrate over d and say, okay, well, what's f? F is yz zx xy. I'm just pulling that off of our definition of f here. And then we are dotting that with this negative z sub x, negative z sub y 1 dA. And you see all the rest of this. This is the p, q, and r. When you evaluate this dot product, you're going to get the formula 10, right? You have p times this, that's negative p z by x. You have q times that, that's negative q z by y. And then you have r times 1, so that's just r, and you add those together, and that gives you, where was this? This expression from the textbook formula. So this handles the dot product, basically. But if you find this to be easier to remember than that, which I personally do, but, to each their own, this is less to remember. You just have to plug things in, and then you'll evaluate the dot product as you go through these, right? You still need to expand z according to x sine y, evaluate those partials, work out the dot product. You will end up with exactly the same thing. There's just, there may be an extra step or two at the beginning as you're substituting and working out the dot product, but like I said, it's a little bit less to memorize. 6 of one, half dozen of the other, whatever works best for you. There's even less to memorize if you have somehow found the time to read section 16.6, because with a good understanding of parametric surfaces, we don't even really need to remember any of this. I like to go with this from a more fundamental level, but it's kind of a spectrum of options there that you can pick from.